We're going to talk about coordinate geometry, everything that you need to know about working with geometry in the coordinate plane. The first thing that we need to talk about is the distance formula, because that's a really big part of figuring out things about figures in the coordinate plane. You need to know how long their sides are, or the distance between 2 points. So your Ames reference sheet again will give you the distance formula, and it looks like this. Given point S, which has coordinates x1, y1, and T, which has coordinates x2, y2, the distance between those 2 points is represented by ST, and it will be the square root of the difference in the x-coordinate squared plus the difference in the y-coordinate squared. So let's look at a quick example. Let's say we have 2 points, A and B. A is at 2, 9, and B is at 8, 1. So if you wanted to, you could label these points x1, y1, x2, y2, and then it's just a matter of taking these values and plugging them into the formula. And this is really nice because you know this formula is going to be right. You're going to have it right there on your sheet. So if you do that, you're going to get x2 minus x1, so 8 minus 2 quantity squared, plus y2 minus y1, or 1 minus 9 quantity squared, which gives you 6 squared plus negative 8 squared. 6 squared is 36, negative 8 squared is positive 64. If you add those together, you get 100. Take the square root of 100 and you get 10. So the distance between A and B is 10 units. Now if we look at that graphically, we can see A is up here, B is down here. Something that will always work for finding the distance between 2 points is the Pythagorean theorem. I mean, that's really all this formula is. It's just using coordinate points and plugging them into the Pythagorean theorem. So if we look at this diagram and we wanted to find the distance between A and B using the Pythagorean theorem, just draw yourself a right triangle, and it's as easy as counting the distance or counting the segments or units on each side of the triangle. So this side of the triangle you could count and see it was 8 units. This side you could count and see that it was 6 units. You can set up the Pythagorean theorem. 8 squared plus 6 squared equals c squared. And again, you're going to get 10 for that hypotenuse. I really like this method. It's going to work every time and you're familiar with it. If you like formulas, use this method. Make sure you label your points so you plug things in the right order. Okay, next, midpoints. Midpoints are really easy, but it's a formula that people forget a lot of the time. So instead of remembering a formula, remember this. It's just the average of the coordinates. If you want to find the halfway point between two things, that's just an average. So what you're doing is you're finding the average of the x-coordinates and the average of the y-coordinates to make a new coordinate. If you don't like that, you do have the formula on the Ames reference sheet, but it's showing you that you have an average. You add the 2 x-coordinates together and divide by 2. You add the 2 y-coordinates together and divide by 2. So let's look at an example here. If we wanted to find the midpoint of AB in this diagram, where we have A and B right there, we're going to look at the diagram and identify that the coordinate of A is negative 6, 5, and that the coordinate of B is 8, 3. So this is your x1, y1, x2, y2. Plug those straight into the formula, or just find the average of your x-coordinates. So negative 6 plus 8 over 2. Average of your y-coordinates is 5 plus negative 3 over 2. Both of those give you 2 over 2. And if you simplify that, you get the coordinate 1, 1. You should always go back on your diagram, plot that point, and make sure it looks like a midpoint, which this one definitely does. Let's look at another example of how you're likely to see a midpoint problem on the Ames. Let's find the midpoint of XZ, of segment XZ. And we see this figure here, which is a parallelogram, and we want to find the midpoint between those 2 points. We can see in the diagram it's not going to be a nice whole number midpoint, but let's just take a look at it. The coordinate of X is 7, 4. The coordinate of Z is 3, 3. So the midpoint of XZ, average of the X's, 7 plus 3 over 2. Average of the Y's, 4 plus 3 over 2. 7 plus 3 is 10. 10 divided by 2 is 5. 4 plus 3 is 7. 7 divided by 2 is either 7 halves or 3.5. So let's look at that point. Over 5, up 1, 2, 3.5. Yep, that looks like it's in the right spot. In my experience, I've seen lots of problems with midpoints that have fractional coordinates. So don't worry about that. Just deal with the fraction, reduce it as much as you can. All right, another part of working in the coordinate plane is translations. 4 different translations you need to be, or transformations, but there's 4 different ones you need to be familiar with. The translation the rotation, the dilation, and the reflection. So we're going to go over all 4 of those. A translation slides a figure in any direction. So you can take a figure like this, slide it left, right, up, down, whatever. One thing that you need to worry about with translations is how does that affect your coordinates and what is the notation that you use. If you translate a figure up or down, you're going to be adding or subtracting to the y value of the coordinates, right? The y value represents the rise, the up and down. If you translate left, right, you're going to add or subtract to the x coordinate. So let's look at an example and talk about the notation that we use here. So here we have a figure, and we want to translate it down 4 units and right 2 units and find the new coordinates of the vertices. So here's our figure A, B, C, D. A is at -2, 4. If I want to translate that down 4, I'm going to be subtracting 4 from the y value. And if I want to go right 2 units, I'm going to be adding 2 to the x coordinate. So taking this coordinate, -2, 4, adding 2 to the x, -2 plus 2 is 0, subtracting 4 from the y, 4 minus 4 is 0. My new coordinate for A will be at 0, 0. And that new coordinate we call A prime. That prime indicates a translated or a transform coordinate point. Sometimes you might even take that point, transform it again, and you'll see notation like this, A double prime. It just means the second transformation. So if I add 2 and subtract 4 from each one of these coordinates, I'm going to end up with A at 0, 0, B at 5, 0, C at 5, -3, and D at 0, -3. Always plot your points just to check and make sure it looks like it's been shifted to the right and down, which is what we wanted in this case. Many times with transformations, you'll see both a shift left-right and a shift up-down, so you have to deal with both of those. All right, let's talk about reflections. A reflection is going to flip a figure over a line. Most of the time, you're going to see one of 2 reflections. You're going to either reflect over the x-axis or you're going to reflect over the y-axis. You can reflect over like diagonal lines, but that's not as common. If you're reflecting over the x-axis, this is a diagram of what that looks like. So you can see if this was my original figure here, and I reflected that, and it kind of looks like it's upside down. The x coordinates of my new figure all stay the same, but my y coordinates are exactly opposite. So what happens in a reflection over the x-axis, your x coordinate stays the same, your y coordinate becomes negative. So if you had the point, let's say this was the point 5, 2, the new transformed point, let's call that point A prime would be at 5, -2. On the other hand, if you're flipping over the y-axis, you can see the y values are all staying the same, but the x values are getting reversed. So in a transformation that reflects over the y-axis, your x value becomes negative, your y value stays the same. So again, if we had this coordinate, 5, 2, we called that point A, it would go to the point -5, 2. And you can see if you count back 5, up 2, that's in the right position. That would be your A prime. So worry about those 2 reflections, I think, and you'll be fine. We also have rotations. There's not a clear-cut formula to identify a rotation because really it's a matter of trigonometry, but there's some common rotations that if you're familiar with, you'll be able to solve all the problems that you need to solve. So a rotation turns a figure around a point. That point that you turn it around is called the center of rotation. The most common rotations that I think you're going to see are going to be 90 degrees, that's like a quarter turn, 180 degrees is a half turn, 270, 3/4 of a turn, or a full 360 degrees. That center of rotation is almost always going to be the origin in the coordinate plane. So I just wanted to give you a visual of how you could organize your information if you had to identify a rotation. So here's a triangle. If we wanted to rotate that figure 180 degrees around the origin, one thing I do is I try to visualize little circles that intersect each one of the vertices. And so for example, if I'm looking at this point and I rotate it 180 degrees, that's going to go straight through the center and then come out the other side, so that new point would be right here. And I can do that with every single one of the vertices and just think about where is that point going to rotate around on that circle. Get rid of you. Hey, now I want to get rid of you. Thank you. So you're going to rotate all the way over there, and you're going to rotate all the way over there. So this guy's going to look kind of something like that. Those little circles can help you identify exactly where those new points are going to be. So practice with just these 4 rotations and I think you'll be fine. All right, last one is the dilations. And a dilation is when you enlarge or reduce a figure, and the figure is enlarged or reduced from a specific point, which is called the center of dilation. And again, that center of dilation is almost always going to be the origin, at least for the problems that we look at on the Ames. The scale factor is what we enlarge or reduce your figure by. So for example, if we doubled our figure, the scale factor would be 2 if it was twice as big. If we cut it in half, then your scale factor would be 1/2. So let's look at an example. Let's dilate the figure by a scale factor of 1/3 about the origin. So since you're dilating it about the origin, you're not moving the figure and shrinking it, you're just taking it and shrinking it in place. It's really easy to do this. All you have to do is multiply all your coordinates by 1/3, because that's the scale factor. It would be different if you were dilating it around a different point than the origin, but I haven't seen any problems like that on the Ames. So for example, if h is at -6, 6, multiply both those coordinates by 1/3. -6 times 1/3 is -2. 6 times 1/3 is 2. So my new h prime, is going to be at -2, 2. My new j, 1/3 of 9 is 3. 1/3 of -6 is -2. So my new j will be at 3, -2, which is not right there. It's right there. My new I, 6, 6, will be at 2, 2. 1/3 of 6 is 2. So that is right here. And my new k, -9, -6, will be at -3, -2. So -3, -2. Make sure you draw in your dilation to make sure it looks exactly like the original figure. A dilation will always be similar to the original figure, but not congruent to the original figure, because it's either going to be bigger or smaller. All right, that's all you need to know for coordinate geometry. Think about how you can put some of these ideas together. Look at dilations, transformations, and distance in order to identify things about your figures.